What's up? Short lesson. Um, because the best way to kind of learn these things is to do some of the problems. So, what we're going to do is just kind of introduce these rate problems. And that's what we're learning is rates. And what we're going to realize is it's similar to what we've already done. And we're going to like do homework problems to help us understand uh, the lesson. I'll show you. Okay. So, Unit 8 is all about.
Food is here in the upstairs main teacher's lounge.
Unit 8 is all about taking us from like position, velocity, acceleration and bringing us back to FF prime, F double prime. And this first lesson helps us understand that it's just not all positions, velocities, it could be any derivatives. And then the next lesson helps us understand like we could be talking about F's. Okay. And we're going to use the stuff that we learned. And here's the key from last unit that's gonna like be taken with us forever. Like the biggest lesson that we learned last unit. That if you have a derivative, you know that v is x prime, and you did your sign analysis over a closed interval, you got negative, positive, negative. Like this is stuff we used to do back in unit 3. We'd analyze the signs of a derivative. Okay? And let's pretend those weren't there. We know that that tells us that x is decreasing, increasing, decreasing, right? But if we have areas under our derivative, areas under derivatives, the areas under our derivatives tell us how much we're going down, how much we're going up. And let's say if we are given, say, an initial function value or initial position, we can use these areas to find future positions. We could say, oh, x of 1 has to be 4 because I go down 1. X of 3 has to be 8 because I go up 4. X of 4 has to be 6 because I go down 2. This is how we find maxes and mins, okay? So that areas or accumulations of derivatives equals change in totals. Okay? How much my total x is changing. Okay? Now, what's another word for derivatives? You could say slopes of tangents. You could say rates of change. Okay? And how this is going to be applied to today is we are going to be given some rates. Well, accumulations of rates, areas of velocities, change in position. Accumulations of rates, change in totals. It's like, think of x as being like a function, a total. Area under its derivative, a change in our total. Okay, areas under derivatives, we could use f prime, change in totals of our original function. Okay, because let's look at some problems that you're going to see on your homework. These problems, at first glance, seem extremely complicated, okay, and extremely wordy. I don't know which one I'm going to do. Fish? No. I'm going to do the rainwater question. Okay, so let's read this question. And we're focusing on these questions. These are actually full-on free response questions from past tests. So we're just taking a lesson to prepare ourselves for these free response questions. On your test, the Unit 8 test, which is only 2 lessons, there should be 2 problems like this. There should be 2 problems like the other lesson that we're about to learn. Okay? So let's read it. It says the rate at which rainwater flows into a drain pipe is modeled by the function r, okay, capital R. Capital R of t is 20 sine t squared over 35 cubic feet per hour. That's a helpful hint. From 0 to 8, the pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate, d of t, which is that, cubic feet per hour, from 0 to 8. There are 30 cubic feet of water in the pipe at t equals 0. How many cubic feet of rainwater flow into the pipe? Is the amount of water in the pipe increasing or decreasing? When do we have a minimum amount of water in the pipe? And then we got these questions like, we can hold 50 cubic feet of water before overflowing. If water continues to flow in and out, like write an equation. It's like, oh man, this seems really tough. But it's not, okay? Let me go back to our notes. Rates. Rate that water flows into the pipe. Rate that the pipe allows water out. In what type of units? Cubic feet per hour? Cubic feet per hour, you read for those? Some others. That's a velocity. That's a derivative. Rates are derivative. Okay? So it's confusing to students a lot of times because you're used to like capital R's, like that's a derivative? Yes. This is a derivative of some sort of function. I don't know what it is because I can't take its antiderivative. That would be able to tell me how much total rainwater has flowed in. Okay? The antiderivative of d would be an equation that would be like a total. It's almost like r is a velocity and its antiderivative being a position, but the position would give me how much has flowed in, how much has flowed out if I took the antiderivative of that. Now, unfortunately, I can't, okay? But I can think about that. Like the antiderivative of r would be like the total or like the position of the total, the position of how much has flowed in. And the antiderivative of d would be our total flow out. But we can't. We can't take the antiderivative. But what can we do? We can find an accumulation using our calculator. I don't know, from like 0 to 8 of r. And this can be plugged into my calculator. My calculator can accumulate my rate. The accumulation of my rate, the area under my rate, is going to be the change in my total. Okay, R stood for the total, the rate at which the water's flowing in. So this would be the total that has flowed in. I could do the same thing for D. Let's say this was D. It's not D, but let's say it's D. If you did an integral and you use your calculator of 0 to 8, you'd get your change in your total or your total that's flowed out. Okay? And that's what's going to help us understand. It's like, oh, that's the whole how much has come in, how much has gone out. The areas under my rates will give me how much. How much. Now, it's going to be a little bit different though, because all of the other questions that we had from last unit, you're given one velocity, you're given one derivative, you're given v. But here we are given 2 velocities. We got a velocity in and a velocity out. We have a rate in and a rate out. Okay. What that means is this, if we're thinking about like the total water in, how much that has gone in has got to incorporate two of my velocities. And it gets a little bit more confusing with this, but let's think about it. Okay, then let's think about what the question. And I'm gonna do part A and part A2. Part A is how many cubic feet of rainwater flow into the pipe, and then part A/2, I'm gonna say is how much water is in the pipe. Okay. Now, a lot of people, again, they haven't done these problems before. They read the question, they're like, the rate at which rainwater flows into the drain pipe is modeled by R over the 8 hour interval. A lot of people think, let's plug in 8. And they're like, okay, I'm going to get 20 sine 64 over 35. Sorry, you just found that water is flowing in at a rate of positive 19.339 cubic feet per hour. That's how quickly water is flowing in. That's the velocity. It is not a total. But we will remember that areas under derivatives, accumulations of velocity gives us how much we change in totals. And you're not going to plug in 8 to this. Instead, you will use your friend, Mr. Accumulation and Mr. Calculator, because you can't take the antiderivative. These are all calculator problems, by the way. And Mr. Accumulation of this rate gives us the total in 76.570. This is in cubic feet. How do I know? We are accumulating cubic feet per hour times hours. If you do cubic feet per hour times hour, boom. That's the accumulation. That's the math that your calculator's doing. Okay? All right. So my answer to part A, how much flowed into the pipe, is this 76.570. But now A/2 is a little bit different. It says how much is in the pipe total. Okay. Well, do you remember like how I'd ask you, like, hey, here's x of 0, that's 2. Here's some crazy v. What's x of 4? What'd you have to do? Well, you would like, oh, I could take the antiderivative velocity, get a position function, and find c. Sure, if you could, but you can't. V's crazy. It's like one of those sine e to the x's ones. So what did we have to do? We had to use this new friendly formula, my unknown position, or my future position equals my starting position, plus my displacement, which my calculator can calculate by accumulating velocities, right? And this came from the whole 2 ways to calculate displacement formula. The x of 4 minus x of 0 is the way we do it, using an antiderivative. But your calculator can do this, and all of a sudden, like using that, you have this formula. This is how we're going to figure out how much total's in the pipe. Now I'm going to incorporate this new function. I'm going to say we got T of T. Capital T stands for total. Think of it as like a big X, like a position. Okay. And this is what I'm going to represent the overall amount. Okay. Now, what do I need? An initial amount. Okay, that's like my T of 0, or this 10 gallons, or over here in the question, there's 30 cubic feet of water at time 0. So my initial amount, which is 30. But then I need to add, my displacement. I need to add the areas under my velocity, the accumulations of my velocity. But I have 2 velocities. I have a velocity in and a velocity out. how can we incorporate both of those velocities at the same time? There's two different ways. I'm going to give you the way that will always work, no matter how the problem is oriented. Here's my initial. Let's add the total that has flowed in. I'll call it the total in. What do? I will find the area from 0 to whatever time I choose of my rate in. Okay, that will give me like, I started with this much water in the pipe, this much water flowed in. So I start here, I added this much, boom, that's how much in the pipe. But we also have water draining out. We have a velocity out. So guess what we're going to do? I bet you can get it. We're going to subtract the total out. Well, how do we get the total out? Well, we will find the accumulation from 0 to whatever value we choose of the rate out. And that's like the velocity out, the velocity in working together. Okay? And that's what I got here. It's like your initial, total in, minus total out. Okay? Cool. And that's how I'll find values of the total. Just use my calculator. So let's do that for this problem. And then we'll talk about like maxes and mins and stuff like that, right? Cool. So I want to find t of 8. I will start with t of 0, which is 30. I will add 0 to 8 of r, which is my rate in. It's a derivative. I'll subtract 0 to 8 of d. It's my rate out. It's my other derivative. This is all you need to write down for these problems, but to do the work, your old friend Math 9 is going to help you. Fortunately, I already have the total in. Okay, so that's in. So I got 30 plus, why don't we just find separately the total out? 0 to 8 of my total out, negative 0.04 t cubed plus 0.4 t squared plus 0.916. Unfortunately, these calculator problems are going to be more like intensive. So 30 plus my total in, accumulation of my velocity in. My calculator does that. Minus accumulation of my velocity out. Boom. 48.543. Okay, great. That's how we can find totals. Very much a formula that we used last unit. Okay, just applied differently. So it looks different, but it's the same stuff that we did. Now, what is going to be new is maxes and mins, increasing, decreasing. Okay, in the last unit, it's all about, what is your velocity? If I know my velocity, positive, negative, I know, x prime can tell me about x, increasing, decreasing, and then like the areas under my velocity told me how much I'm going up and how much I'm going down. Great. Here's our problem. I got t, my total. Okay, I got to figure out when my total amount of water is increasing or decreasing. Let's read the next question. Is the amount of water pipe increasing or decreasing at t equals 3? Okay. Well, I need to look at the derivative of the total, t prime. I need the velocity of my total. Well, here's my expression for my total. My expression for my total is always initial amount plus integral, a to b of my rate in, or 0 to t if I'm going to be more precise, and this is important because we need to start getting used to using variables and integrals because it'll pop up a little bit more often, solving equations and stuff like that. We're not used to it, but it makes sense. Like at a time, okay, at a time, okay, cool. So that's it. What would be t prime? Well, this is just a number, so its derivative is 0. We know that this is like a velocity, and that if we take the integral of it, we got to change in a position, right? Well, how do you take an integral? What does this mean to a human being? This integral doesn't mean accumulate, it means take the antiderivative, right? Okay, so, and I get like x of b minus x of a, right? But let's pretend it's just an integral. It's just like I take the antiderivative. Well, what would happen if I took the derivative of an integral? What would happen if I took a derivative of an antiderivative? Well, the integral would go away. What you would get is just your rates, your velocities, your v's. Oh, t prime is my rate in minus my rate out. We just found a formula that is going to be the velocity of my total. You think of this as v, but since there's two velocities at play, well, subtract the out from the in, that's your overall velocity. That's what we're going to have to do. Look at like rate in minus the rate out. And if that's positive, my amount of water is increasing. If that's negative, the amount of water is decreasing. It's the same stuff. And then again, uh, if you look at your integrals of your rate out and subtract your integrals of your rate in, that's how much you're going to be adding, and that's how much you're going to be subtracting. You can do it separately. We could also do it together, but we're going to be careful about doing it together in one integral. Why do I say be careful? Because sometimes like the intervals will be different. Sometimes you'll do your rate in from like 0 to 5, but your rate out will only start from like 2 to 5. So I like to keep things separate just so we don't make that mistake. Okay. And so that's what I'm going to do. Like, hey, the question here is increasing or decreasing? Well, literally, is t prime positive or negative? That'll tell me if t is increasing or decreasing. Most students actually get this answer intuitively because what they do is they find r of 3 and they compare it to d of 3. And they're like, oh, if the rate in is bigger than the rate out, then I'm adding. And that makes sense. Well, let's think. If this is bigger than this, and I subtract them, what's going to happen? We get a positive number. If you get a positive number, the amount, a positive number for a derivative, the amount's increasing. So I go and just go ahead and subtract them. You could compare them. You could say the rate out is bigger than the rate in, blah, 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 blah. That's fine. Uh, Unfortunately, like this is more stuff to type into your calculator. There's my rate out. You can compare it to your rate in at 3. Now notice I haven't graphed anything yet, but I could if I wanted to, and I will for the next problem. And it's like intense, and you'll see there's like a lot of stuff to type in. You got to make sure you're careful when you're typing things in. And you get 5.4. The rate out is bigger than the rate in, decreasing. Or R of 3 minus D of 3 is negative. T prime is negative, T is decreasing. Okay? Now, let's do part C. I do part D in the video, the homework video, and I'm just going to stop the lesson after this because that's it. It's perfect. I'm going to go get some Chick-fil-A because it's 5:20 and I'm staying here for a calf showcase even though there's no school tomorrow. Isn't that great? Um, when is the amount of water at the pipe minimum? Well, guys, this is like just like last problem. When are we furthest left? It's like, oh, let's analyze velocity. When velocity changes sign, and I'll look here because that's when my positions decrease. It's the same deal. It's the same deal. Only we're gonna have to look at t prime, and we're gonna have to graph t prime. Now, t prime isn't given to you. You understand what it is. T prime, that's like v, that's like x prime, is my velocity in minus my velocity out. Okay? Now, you could look at both velocities separately and kind of understand what's going on. I prefer to do it like this because then it just like makes sense with all the number lines that I've done. I'm going to fix this number line so it's perfect. Sorry, this was supposed to be a negative. I'm going to fix the number line so it's perfect to my situation, and I'll be able to go from there. So we're going to go in, and it's different than last unit when it's just the velocity. We need to graph the first velocity minus the second velocity, not necessarily the first one. The velocity in minus the velocity out. Okay, velocity in minus, use a big old set of parentheses here, velocity out. And like this is annoying and this is intense. And like, yes, it is. You're right. And there's a lot of stuff you're typing in. A lot of times when students like type in so much, they just assume they're doing something wrong. No, this is it. Okay, we're going from 0 to 8. Oh, very similar. Adjusting our windows. We probably should zoom fit. Remember zoom fit? We haven't used zoom fit in a while because everything fit in the negative 10 to 10. But I'm going to use zoom fit just so I can see perfectly t prime. Honestly, that would have fit negative 10 to 10. But it's beautiful. Okay. Now, what's this show? T prime. That's x prime. That's v. That's what we're used to seeing, what we're used to looking at the graph of. Okay. What do we see? That intersection where t prime changes signs from negatives to positives, right? Cool. What else do I see? This accumulation would be how much water has left, or the decrease in my total. This accumulation is the increase of my total. How do we find when we have maxes or mins? Is this part C? You can say T is going to be a min. Where? When T prime equals 0 or an endpoint. There's your candidates. Here's the candidates test. T of 0 I know is 30. T of 8 I already know is 48.543. I need to figure out what T of A is. What's A? Make sure you write it down. I feel like people aren't doing it. Second, calc, intersect, enter, enter, enter. 3.271. Let's store that. Okay. Start with your original value, add your displacement. And literally, if you have T prime written down, you can use T prime. Ooh, gosh, I'm so used to using X of 0. I got to switch it up. It's T of 0. Be careful. It's like the same stuff, though. It's like, I got it. I got the thing I use so often last unit, hopefully correctly. Why don't we just do it here? Second calc, 7, 0 to A. Boom. That's how much I'm decreasing. T is decreasing then increasing until I should have written that number. But -2, that's how much I'm going down. I'm going down -2.354. Not much. Take that answer, 3.271. I have to write that down. A equals 3.271. Oh, write it over here. A equals 3.2716584. That's when t prime equals 0 at this time. And then make sure it's put t and then equals A. Boom. And then that's how much I'm going down. I could take my answer, which is my displacement, add it to 30, and boom, 27.964 is how much water is in my tank or my pipe or whatever. Now let's get this 48.543 a different way. Uh, let's find my displacement from A to 8. This is just like last unit again. We're just doing it different ways, and then we're going to bring everything back to FF prime, F double prime. I'm adding 20. So I take this, add my answer, which was the 20, and there's my 48.543 a different way. Okay, so I only drop 2 cubic feet, and then I add 20 cubic feet of water. When's the min? T prime is 0 at endpoint. You didn't have to check this, but you already did the work. And you could have just said at t equals A. Why? Because t prime is negative, then positive. Negative from 0 to that time, 3.27, and then it's positive from 3.27. So it has to be the min. But that's it. So this is a well-timed lesson because it's so much like what we just did. Okay. So the biggest difference being two velocities at play. Well, that's okay. Rate in minus rate out. Adjust and adapt. Make sure you understand this lesson. Make sure you try the homeworks. Don't just copy off the video. Later.